we have these three parametrizations, right? And it turned out that the first part is we observed that these were all parametrizations of a portion of the same algebraic curve, right? These all parameterized portions of the curve x squared is equal to y cubed. And for your convenience, this is what the curve looks like. In general, we'll talk about this, but it's in general pretty hard with a parameterization to picture what the curve looks like. Especially if you could reduce it to something algebraic like this, but in this case, unless you're really good with your geometry already, then it's probably hard to off the top of your head see what this curve looks like. It turns out it looks something like this. This is a curve x squared plus y cubed. But even though you don't know what the exact curve looks like, you can still deduce sort of what the behavior is of your parameterization. So assuming now you see a picture like this, where this is the algebraic curve, right here. Does someone want to, maybe volunteer in chat, what the behavior, what's different between A, B, and C? The rate. All right. So the rate in the meaning of speed, yeah, we'll go into the issues of speed correctly, but what about the portions of x squared equals y cubed that's covered by, say, A, B, and C? So in this case, right, let's say the region of parameterization for t at least is from minus infinity to plus infinity. So in A, it should cover this entire curve, right? At t, as t tends to minus infinity, you see that x is equal to t to the t cubed, right? So t, as is from minus infinity, you're starting way off over here somewhere. You're coming back here. At t equals 0, you're at 0, 0. And then as t moves on to the positive reals, right? T cubed stays positive, so t cubed is x. So x stays positive, y grows like t squared. So you're going to be tracing from here all the way here, and then forwards again, right? So if you look at what the parameterization in A is giving you, you're coming in from here, and you're going back out again, right? So parameterization A covers the entire curve x squared is equal to y cubed. Did I get that wrong? Yeah, x squared equals y cubed. Moves minus infinity to positive infinity in x. All right, so you're going from left to right here is what this curve is doing. Gabriel says A will cover the entire graph for all values x, right? That's correct. And B and C will only cover positive x. Right. So that's a good observation, right? We see that in contrast, if I now look at the parameterization, let's start with B first. We see that x is t to the sixth, right? And you're an even power of t, so it doesn't matter how negative t is, you're always going to be positive, right? So what's happening here is if you look at the parameterization in B, when t starts, when you start your clock, way back in time in minus infinity, your x value is very large. It's close to x, tends to have positive infinity. And then as t shrinks from, the negatives into 0, you're going to approach 0 in x. So that means you're going from all the way up here at minus infinity, you're going to go here, approach 0. At 0, you're going to hit the origin. And then at t to this, and then as you get larger again, t to the 6 is going to grow again. And then you're going to go back out again. So what's happening in B, just by looking at, assuming what the algebraic curve looks like, which is this, this parameterization, just by looking at the behavior in x and the limit of the function in t, you see that as t, this parameterizes just the right portion of x or equals y cubed. And it parameterizes in such a way that you move from out here into here, and then as you hit the origin, you bounce back along the curve from where you came from. All right, so in contrast, in B, your parameterization only covers the curve x squared is equal to y cubed for x greater than or equal to 0, because t to the 6 is always non-negative, and it moves from x equals x near positive infinity to the origin and then back out again. So this is completely non-rigorous mathematical language, but I'm just trying to illustrate to you guys what's happening here, right? So here starting here, going back in, and then bouncing out. So you're going something like this, right? That's roughly what's happening. It's very difficult to draw, so I'll just draw something like that. All right, and hopefully you'll see that you initially go this way, and then you bounce out that way. So we have a question in chat. What is the difference between parametrization versus just normally plotting the equation on the graph? Okay, so that's a good question. We'll get to an example pretty soon. Not all equations can be given like graphs, all right? Remember, for you to be a graph, first of all, you need to obey the vertical line test, right? For every value of x, you have to have a corresponding value of y that's unique for it to be a graph. Now, the simplest example is a circle, right? If you have a particle moving in a circle, there's no way for you to graph a circle other than, parameterizing it two ways as a graph and pasting it together. So one reason is not every path can be written in 2 dimensions, can be written as a graph. So not every path in 2 dimensions can be written as a graph. We'll also see soon examples of paths where you could self-intersect, all right? There are, if you think of a circle, really, when you maybe, if you think of a circle that looks like this, then you could say you self-intersect here, or if you imagine sort of a figure 8 curve, if you go like this, if this is the particle movement, then not only is it not a graph, it fails a vertical line test, but in fact, it could hit the origin multiple times at different, several times at different times. And you could never represent the fact that it's, it hits a single point multiple times, depending on your time, without a parametrization. So a parametrization really gives you finer details than just a graph ever will. Or, you could also have algebraic curves that are not graphs. But even then, for example, you could probably write the figure 8 curve as also in an algebraic relation satisfying this. It's not going to be a graph, but even then, I can't tell you how many times a particle moving along that path is going to intersect itself or hit the origin without giving you a parametrization. All right, so hopefully that gives you motivation to consider parameterizations. Okay, Mitsuka says, right, why do you go back to the origin and back out again? So remember, for all 3 of these parameterizations, my domain in time, so think of this as a stopwatch, right? The history of a particle goes from minus infinity to plus infinity, exists for all time. Back in time at minus infinity, this is very positive. This is still positive, near positive infinity, so I'm out here somewhere. As t goes to 0, this goes to 0, right? T to the 6, it shrinks and shrinks and it hits 0. At 0, your curve is at time equals 0, you're at 0, 0. So it must hit 0, 0 here. And then as soon as time goes positive again, you must shoot back out against the curve here because everything's positive again. So, right, so let's go back. So Gabriel also pointed out that C has a similar issue. You're only doing portions of the curve here in C. Right, so in this case, C, you also, which portion of this curve is covered in C? Is it the positive? Is it x is positive, x is negative, the whole thing? Right, it should just be the x equals positive part once again, because remember your exponential function here, it doesn't matter how negative your exponential is, e to anything negative, that's still just something positive, right? It's just something very small. So both x and y, right, here are positive. Really here, because we know the graph looks like this, we only need to care about what x looks like, but x is always positive, right? E to the minus 3t, doesn't matter t is negative or positive, it's always x is going to be positive. So once again, only the right half, it's going to be strictly positive. Actually, something funny happens here because, yeah, it's actually, no, when you said positive, that was actually right. Non-negative is incorrect because e to the minus 3t could never actually, unless you take t, be actually equal to minus infinity, which is not positive, which is not possible. E to the anything, your exponential could never actually be 0. So x could never be 0. You'll never actually hit the origin here in this parameterization. That's one thing to see. So now let's look at the behavior of what this parameterization is telling us. Way back in time, when t is close to minus infinity, this is e to the minus 3t, right? So if you're at minus infinity, minus 3t is close to positive infinity, right? It's close to 3 times positive infinity, which is positive infinity, right? So this exponential here is very, very, very large, right? It's going to be plus 3 to something very big when t is close to something very negative. So this tells you that way back in time, you're starting way out here again, right? X is way something huge, right? It's something starting off close to x is positive infinity. And then as t, as t increases from something very negative to 0, right? Your exponential is e to something very much less and less positive, right? Until you hit e to the 0, which is 1, right? So at some point, at t equals 0, your parameterization is actually going to take you e to the 0, which is 1. So at x equals 1, that's where, wherever x equals 1 is, and the corresponding y, which is also 1, that's where at t equals 0, this parameterization is going to hit you. So this model is a particle that goes all the way here, way back in time. It comes here at t equals 1, or at t equals 0, rather. It hits this point. And then as t gets way more positive, what happens? Well, as t increases positively, e to the minus 3t gets more and more negative, right? So you're raising e to something more and more negative, approaching e to the minus infinity, which is, at e to the, as e goes, exponentiated more and more negatively, it gets closer and closer to 0. It never actually reaches 0, but it gets closer and closer to 0. So what's happening here is you have a particle starting way out here. You move and you move, until finally, well, you never actually reach the origin, but you just move out all the way from here until, closer and closer to the origin. You don't reach the origin, you don't bounce back out, but it does trace out the right half of your curve here, right? So let me write this down. In this case, we pointed out that this is a particle traveling, at some point out here, it comes in, and it never actually hits the origin. All right, it just goes one direction, does not bounce it back out, does not hit the origin. It does actually, you can check that at x equals 1, y equals 1, this corresponds to, this is a point, this occurs at t equals 0. You get the point is equal to e to the 0, which is 1, 1. All right, so we hit this point precisely at time t equals 0 in this parameterization. And then you go on your way. All right, so parameterization B only covers x squared equals y cubed for x strictly greater than 0. So not x equals 0. Moves from x near plus infinity to x near 0 asymptotically, and it never reaches 0. All right, so these are 3 parameterizations where they all figure to be part of the same curve algebraically. They satisfy the same algebraic equation for every point, but they parameterize very different portions of this curve, and they also travel along their paths very differently. Okay, so let me look at the chat for. So Robert says the definition of a parameterization, right? So the definition of parameterization, going back to last time, is right. So the definition of parameterization we're going to take as here. So these are, formally speaking, these are functions of one variable to 2 variables. It could be functions from the entire real line, which we just saw, into R2, or it could also just be a function from a subset of the real line, so just an interval from A to B to R2. And they're frequently written as x of t, y of t, which is usually the way that we present things. All I'm saying is, this is a very nice definition of what a parameterization is. They're a function not of one variable, but one variable, 2 variables in this case, or later on 1 variable, 3 variables and more. But the reason we care about such functions because they're very nice to model paths with, all right? It's no use having something abstract like this, but the intuition here is they're useful precisely because they're good at telling us how particles move and the trajectories. All right, so that's what the parameterization is. All right, so in this particular exercise, it turns out that we're given a parameterization. In fact, we're given 3 parameterizations: x of t, y of t equals t cubed t squared, and then 2 different ones. And the point of this exercise is you want to imagine what these actually tell you geometrically, right? A bunch of, the point, I mean, it gets lost, but the point of calculus really is it was invented, right, by Newton and others to describe, how particles move in real life, how to describe physics and all that. And the point of parameterizations is precisely to model paths. So we cared about what precise path these things model. So in this case, the step to imagine what a path, parameterization models is usually you want to reduce it down to an algebraic equation, something we're familiar with. If we were lucky, maybe we could have gone something like a circle, like x equals y squared equals 1 or something that these all obey. Unfortunately, in this case, we got something that's slightly less nice, but still imaginable. And I'm just pointing out that if you even know what the algebraic equation a given parameterization satisfies, if you know the algebraic equation and you have a sense of what this algebraic curve looks like, then you could do further analysis, which is what we've done here, to say, first of all, which portion of this algebraic equation is being covered by this parameterization, and finer details like where does a particle start, where does it end up, at what time does, at what particular time, for example, does a particle hit a point, things like that. And yes, we'll eventually be doing parameterizations and in this class, mostly from 1 variable into 2 variables or 3 variables, all right? So the max is probably 3 in this class, but you could see how this generalizes. And the point of it generalizing, you could go in 4 variables, and that's the realm of general relativity, right? The theory of gravity. If you remember any intro physics class you've taken, theoretically, we all live in 4-dimensional space, at least, according to relativity. The paths of free-falling observers follow trajectories in this 4-dimensional space. So in essence, you actually have to parameterize. You have a parameterization for 1 variable into 4 dimensions, and your parameter in that case is called your proper time. And then you do various calculus tricks and some tools that we're going to develop in this class to analyze that situation. So that's what parameterizations are. But you should always imagine parameterizations, mathematically speaking, they're just functions from 1 variable to more variables in a certain sense. But geometrically speaking, geometrically the intuition is much more rich. Okay, so Murph says if you trace B and C with time, what's the difference? Right. So let me reiterate the difference here. First of all, you'll note that in B, when you trace time, you actually reach the origin in B. Not only do you reach the origin in finite time at t equals 0, you precisely hit the origin at time equals 0 because you're at 0, 0, so you hit the origin in B. You go here at 0, 0, you hit it, and then you go back out, right? In C, you never hit the origin because you can never reach positive infinity. The limit as e to some let's say e to the minus 3t as t goes to positive infinity, the limit of this is 0. But just because the limit is 0, it doesn't mean you can never. The point of the limit is you can definitely never reach positive infinity. So for all finite time, you're trapped strictly greater than 0 in x. So you'll never actually, for any time you can imagine, you can never actually hit the origin. All right, you get asymptotically closer to the origin, you'll never hit it. Does that make sense? Any other questions before I move on? Right, so B, you bounce back out. C, you never bounce back out. In fact, you never reach the origin, you just keep going closer and closer to the origin and never reaching it. Okay, so hopefully that exercise illustrates the wealth of parameterizations there are for even just one given algebraic equation, all right? So the moral, once again, is different parameterizations can satisfy the same algebraic equation, but behave very differently. Yeah, so do we need to know how to graph the algebraic expression? No, you don't. Well, look, if it's something simple like a parabola, like y is equal to x squared? Yes, right? Y is equal to x cubed? Yes, that's sort of fair game. Even y is equal to like the square root of x, or you do x equals y squared, right? That's a sideways parabola. Simple things like that, I would expect you to know how to graph. But in a sense, you know, those things, no, like the x squared equals y cubed. I don't expect you to know off the top of your head what that looks like. All right, maybe the best you could do is y is equal to x to the 2/3. All right, so maybe you should have a sense of, you know, what x to the powers look like, roughly speaking. But I wouldn't expect you to know off the top of your head what these graphs are for complicated expressions, and I wouldn't test on very complicated curves at all. 10.5, we're going to explore some sort of, you know, parabolas, circles, ellipses, and hyperbolas to a minor extent. Those are like, you know, if you see anything you don't understand from what I present in that section, then you do need to understand roughly what we present, but I'll make it pretty clear. All right, so that's pretty much it. In this particular case, when we trace out the parametric equations, we only cared about the x value because we knew what the graph looked like. All right. In general, you could also do the same thing with well, it's hard with the y value. The y value doesn't give you any information on what the behavior is in this particular case, because for the algebraic curve here, we know that the curve itself looks, you know, y is always positive, right? Because y cubed is always x squared is always positive. Y cubed has to be always positive, which means y has to be always positive. So the behavior of y is uninteresting. You're always going to have positive y. If you look at the asymptotes in t, you're not going to have much intuition. Like in b, I could say, okay, at minus infinity, y is very large. At positive infinity, y is also very large positively, but that happens in both ways in y. So I'm getting no extra information. In this particular case, we only focus on x because of this particular situation, where x is really the only interesting parameter that we could deal with. The best way to practice parameterization is to do a lot of them. All right, so a good way to start is a WebAssign, and then do related problems in that. This is very dry, right? There's nothing intrinsically interesting in parameterizations other than modeling particles. It's what we do later in this course, which relies a lot on parameterizations. That's important for you to be comfortable with these parameterizations. So the more you practice both just on parameterizations and doing other things in this class, the more comfortable you are with parameterizations. So in that case, it was pretty hard for you to actually get off the top of your head what the curve looks like, but let's try what is the curve traced out by the following parameterization. Let's say you have a parameterization given to you by x of t is equal to t squared minus 3, and y is equal to t plus 2 for t between minus 3 and plus 3. So let me give you a few moments to ponder this, but let me give you maybe two subsets. The first one is to eliminate t to find, eliminate t to find equation just in x and y. And then once you get the shape of this, then maybe you should identify features like start, endpoints, direction, or travel. Right. So I would not recommend making a graph of t, x, and y. It's very unhelpful in these situations to get an idea of what things look like. So let me give you maybe a couple minutes, get bounce some ideas off, maybe one another if you want to chat, or think about this for a bit, and then we'll go over this in a couple minutes. All right, so we have a suggestion in chat. Some people are agreeing. That's good. Right. So let's try and go over this example. So if you look here, it looks like in this particular case, you have a linear y is equal to t plus 2. So this seems easier to express. You know, you want to eliminate t, right? So maybe we could substitute t with y instead. So first we observe that y is equal to t plus 2. This implies that t you could re-express in terms of y minus 2, right? Just moving the 2 around. And from the first equation, x is equal to t squared minus 3. You get x is equal to y minus 2 all squared minus 3, which is now what? This is y squared minus, let's do plus 4 minus 4y minus 3. right? And this is y squared minus 4y minus 3. What people got? No, not what people got, because I screwed up. I couldn't do math. It's 4 minus 3 is 1. Okay, there you go. By the way, yeah, okay. I've been known to make several horrible arithmetic mistakes, so please yell out in chat or something when I make these. So here we go. This is the equation here. Now, qualitatively, what shape is this? Is this a circle? Is this a line? What class of curves is this algebraic equation? Right, yeah, so it is a parabola. It's a quadratic, so it's a parabola, right? So you basically have, parabola, refresher. These are things, these are classes of shapes that you ought to know, all right? So, if I just had y equals here and x on this side, it's like y is equal to x squared plus, y is equal to something quadratic, then this is a parabola. It opens as a cup shape, opening up or down, upwards or downwards. In this case, you sort of have the variable switched. So, which way is this parabola opening? Just qualitatively, is this, let's say I have my axes here, x and y. So, if you have a parabola that's like, say, y is equal to x squared, then it looks like this. In this case, we have x is equal to y squared minus 4y plus 1. All right, so which way does this open up? Yeah, it opens up sideways. Is it to the right or to the left? Is it to the right here or to the left? Exactly. So it should be to the right. And the way you see that is by the coefficient in the square term here, right? Because if the square term here is positive, then you open up either upwards if it's y is equal to x squared, for example, or sideways to the right. You have positive, mostly positive behavior in the x direction here. If it's positive, it's negative, then it's going to open it. All right. So a quick refresher. These are classes of functions that you should know. These are parabolas. They're part of 10 point, the rare part of 10.5 that we actually care about. So this is some parabola. This is a parabola opening to the right. Okay, so how do I identify features of this? Well, you could actually go into, if you want specifics on how to draw this, well, one way you could do is, if you want, depending on how specific you're asked, you could identify the roots of this thing, right? If it's a parabola, it's a quadratic, here you can solve for when x is equal to 0 to get the y-intercept, right? So when x is equal to 0, you use a quadratic formula to find the roots of this thing, and you can find the intercepts of this and all that junk, right? But there's an easier way here. You could find where the starting and endpoints are, right? At t is equal to, let me do a different color here. At t is equal to minus 3, right? In this parametrization, you start at minus 3. At t equals minus 3, you have x is equal to 6, and y is equal to minus 1. Here is, well, just to make up this 6 and minus 1, there's something like here, and like here. So this is 6 and minus 1, and then at t is equal to plus 3, you're at x is equal to y is equal to 5, right? So you might have something that looks like this. So this is at point 6, 5, and you start at minus 3 and you go at plus 3, and there's a parabola that looks like this. So roughly speaking, you could say something that, well, okay, so you start here and you end here, right? So it's a parabola that opens something like this, right? So the only remaining feature really is, is it possible for you, does this thing have, 2 roots, a double root here, or no roots, right? So how far does this parabola extend past here? It's possible to do this by looking at the quadratic formula. So you identify any roots of the quadratic using the quadratic formula, or how many roots using the discriminant. So this is a quantity b squared minus 4ac. This is so b squared in this case is what, 16, something like that, right? 16 minus 4. Right, I'm looking at the quadratic here. So this has, this is minus 4 squared is 16, and then minus 4 times this and that. So this is root 12, right? Which is positive, right? So there are 2 roots, which means that our picture here looks like this, right? There are 2 roots, if you don't care about the features of the roots, that's not too bad. It just means that there are two intersections here, and it's going to look something like this. So you start from here, you end here, and you have a parabola that looks like this. There was another example that hopefully illustrates something. So you could also have parameterizations that trace out curves that self-intersect. All right, so maybe before this example, this is a motivating example for parameterizations. Previously, one of you asked, why do we care about parameterizations in the first place? I gave you some sketchy examples. Here's an actual one. Parameterizations can model paths that self-intersect. All right, so here's an example. Consider x is equal to 1 minus t squared, and y is equal to t minus t cubed. This is not something you would be able to graph, but I'm going to tell you I'm going to show you what it looks like. It looks something like this. And there's precisely one intersection. So now that you see, now that I claim this is what the graph looks like, it looks like it hits the origin twice. So at what times does this path hit the origin? The path x of t, y of t, hits the origin at what times? So remember, x has to be equal to 0 and y has to be equal to 0. So what are the possibilities for x equals 0 in this case? Right, so t is equal to, I could have plus 1 or minus 1, because, plus 1 or minus 1, x vanishes. And in fact, in this case, you could factor this out, right? Y is t times 1 minus t squared, so at plus 1 minus 1. This is basically y is equal to t times x. So whenever x is 0, y is 0. So at time equals plus 1 and minus 1, at two distinct times, this particle crosses the origin. And if I give you this, let's do t minus, let's go domain is t from minus 2 to 2. Well, let's have it for all time, right? So here, this crosses the origin at two distinct times. However, I could have another, maybe if I parameterize this to separate a different way, maybe I start here and I end here, or maybe I start here and I end up there. Then if I start here, I can have a parameterization just by having t maybe start at 0 instead. I'm going to miss one of the times where it hits the origin. So the path of that particle is going to be only a portion of this red curve. So it's only going to cross the origin once. So depending on how you parameterize, and also your region of time that you're parameterizing, you get more information on whether this hits, when it hits the origin, if it hits it once or twice, things like that. All right, so that's why another reason why parameterizations are useful. Maybe as a bonus exercise, if this is my parameterization, which direction of travel am I traveling on this curve? Am I starting at y is negative and then ending y is positive? Or am I starting where y is positive and then going towards where y is negative? So here, as t is very, very negative, I have something, y looks like something very negative minus something very, very negative, right? So negative to the cubed is going to be bigger than just negative, but there's a minus sign instead of the t cubed. So when t is very negative, I'm in fact starting where this thing is very positive. While when t gets very, very big, this term, this minus t cubed term, dominates this just single t term. So this is going to overall be very negative. So in fact, I'm traveling something like this. I'm going here, 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 here. So note that in this case, because I have more identifying features in what y can be, I look at the asymptotics for y in terms of time instead of x, right? X, I can't get too much information on what x is. They both start at x is very negative and ends at where x is very negative. So I look at what y is behaving. Right, so direction of travel, let me just mention, as t tends towards the negative, y is equal to t times 1 minus t squared, right? I just factored this thing out. As this gets very negative, right, this coefficient is negative, 1 minus t squared is also going to be very negative. So this is negative times negative, which is a positive. So this altogether tends towards something positive. So as you go backwards in time, your y is getting larger and larger. So, reverse time. So it goes from here down to here. And conversely, as t goes to positive infinity, y is t 1 minus t squared again. Y is t times 1 minus t squared again. Now, in this case, if t is something positive, right, something very large and positive, this coefficient in t is positive. This is 1 minus something larger and larger. This thing's negative. So it's negative times something positive, and they're both growing. So overall, we have minus times positive, that's minus. So this is tending towards minus infinity. And hence y is getting more and more negative. So your curve, your direction of travel, your direction of travel looks like this. Any other questions pertaining to this example? We're looking at y here because there's no good information in x for me to see, right? Because if I just look at what x is, well, as t goes to minus infinity, this is getting more and more negative, right? It's 1 minus something very, very large. And then as t gets to positive infinity, x is also getting very, very large, or in the negative direction, right? Because it's 1 minus t squared. The t squared kills off any sign information you have. They're both, as x goes to minus infinity and positive infinity, x is still tending, no matter what, to negative infinity, right? So I don't know if I'm going this way, the opposite way here, where x is still going to negative infinity, or I'm going this way, where x is also going to negative infinity. I get no distinguishing information whatsoever if I just look at what x is. So I have to rely on what y is. All right, so let me do one more parameterization before we go on to, I guess, the a bit more nuanced parts of what parameterizations gets us. So let's try the following. So let's now look at collision. So depending on parameterizations, particles may have intersecting paths, but not collide. So, I mean, this is another way, this is not too shocking, right? Some of the orbits are, let's just take our solar system, for example, right? Some of the planets have crossing orbits, right? At the path they trace out, these two planets, it crosses at moments, but they're still two planets. They don't just collide with each other. And that's because they occupy, even though their paths that they trace out, do intersect, they don't occupy that intersection point at the same time. So in the same way, two particles can have paths that are, that intersect and collide with each other technically, but the particles themselves don't collide because they don't occupy that intersection at the same time. So let's do an example here. Suppose particles A and B follow paths given by the following parameterizations. So let's say for A, we have x is equal to t, y is equal to t, and I'm going to say t goes from -1 to 1. And let's say B has x is equal to t, y is equal to t. Let's say the time on this clock goes from, let's say, -2 to, let's say, 3. Oh, no, sorry. This is stupid. I forgot this is x is equal to t cubed, and y is equal to 3t to the 6th. The first thing is, do the paths of A and B intersect, and at what points? And B is, do A and B collide? At what times? All right, so we have some suggestions. Let's do part A first. Right, so part A, let's identify whether these paths intersect. So perhaps the easiest way of doing so is to figure out what these curves look like. All right, so for A, we could say this is a portion of the line y is equal to x, right? That's hopefully simple enough to see, right? So it's a portion of the straight line y is equal to x. So that's a trajectory of particle A, and you're going from -1 to 1. And then you have B. What's the algebraic equation that's satisfied by B here? Right, so it should be y is equal to 3x squared. And so this should be an upwards parabola, upwards opening parabola, right? So you want to solve, the intersection is that you want to set x equal to 3x squared, means that x must be is equal to 0, or what's the alternative here? Right, so you could also have 1/3. So your parabola is going to open, your parabola, I mean, it's a very steeply opening parabola, right? Because of the coefficient of 3 in front. So you would have, let's say, x squared, y equals x squared probably looks like this, right? So you want something more narrow that opens up like that. That's going to be the path of 3x squared. X goes from -2 to 3. So let's do something for B. So B looks like and I can't really draw the endpoints in this scale, but you hopefully see the point where if you know, at t -2 is probably somewhere, well, it's probably somewhere up here, and at t is equal to +3, you're probably somewhere way over here, right? So it's you travel from here all the way up there. Okay, so there are two intersection points, and the intersection points are given to you here and here. Now, so part B is, do they ever collide? So remember, for these two paths to collide, they have to occupy the same point at the same time. So if at 0, 0, you have these, first of all, there are only two potential collision points, right? If they don't intersect at all, there's no way they can collide. So you only have to refer to the points where x is equal to 0 and x equals 1/3 and see if they could occupy those positions at the same time. So let me specify. So the intersections here, they intersect at the point 0, 0, the origin, and also at 1/3 and 1/3. Now at 0, 0, they collide because at t equals 0, both A and B are at 0, 0. So there's a collision. Now, what about at 1/3? There is, the right side is not at 1/3, and you can check because at t is equal to 1/3, right? A is at the point 1/3, 1/3. B is at, well, what was it? It was 1/3 cubed. So what? That's like 1/27 and t to the 6. Oh God, I didn't make this easy for myself, huh? So this is at 3 times 1/3 to, well, 1/3 to the 6th. It's like 1/3 to the 5th, right? That doesn't help. But this is not equal to 1/3 and 1/3. So no collision at 1/3. All right, so in this case, you see that the trajectories of these two particles, given the parametrizations, their paths cross at 2 points, but they only collide at 1 point. Let's now take a look at what we could infer from speed and velocity of parametrizations. All right, so here we're moving into a bit more calculus. Let's call this speed and arc length. All right, so suppose we have a parameterization, let's say x of t, y of t, with t between A and B. So I'll just abstractly just drop this out something like this, all right? So this is at x at t is equal to A, y at A. And this is x of B, y of B. Then there's a way for us to associate the speed of this particle. The velocity at time t is written dx dt, dy dt. All right, I'll put these in brackets for now because we're going to cover velocity in more depth later. But if you've taken physics before, then you know velocity tells you the speed of at which you're moving and also the direction that you're moving. And if you've seen some vectors before, then this thing here is a vector in 2 dimensions. Where at a certain time t, let's say you're at time t here, then dx dt is a number, right? So you take one derivative in x, so that gives you a number, and that's the x component of your vector, of your arrow, and this is a y component of your arrow. So altogether, you're going to have an arrow that looks like this at that point, and that's your velocity. All right. If this doesn't, if you haven't seen any any vectors before, then don't worry about this for now. We're about to do this in depth. If you've seen this, then you know that. Well, I'm telling you now that if you have a parameterization, then there's a very easy way to find your velocity at a point, and to find your velocity at a point is just to differentiate in time in each of these components separately. The part that I will tell you, that you should be responsible for this section is the speed. All right, the speed at time t is given by the square root of dx over dt squared plus dy dt squared. And the rough intuition of this is there's a way to rigorously show this, but if you imagine at any given moment here, the speed is the length of this arrow here in red. So at each point in your parameterization in time, you have associated an arrow, all right? And the speed is the length of this arrow. Now, if at this point in time, I have an arrow like this, then the length of this arrow, I could write this in terms of the hypotenuse of a right triangle, right? If I have a right triangle like this, right, then there's going to be the length of this squared, and the length of this squared is going to get me the length of this arrow squared. So I just want the length of this arrow. I square root, the square root of this is going to be equal to this squared plus this squared, all square rooted. Now with this squared, this is roughly delta x, right? It's how much you've moved in delta x. This is how much you've moved in y, so this is delta y. Now, how much you move depends on your change in time. So you got to take the ratios in time. And so roughly speaking, the length of this is going to be, when you shrink everything infinitesimally small, you're going to get this squared plus this squared, all square rooted, and that's going to get you the length of this arrow here. All right, so completely non-rigorous way of seeing this, but hopefully that gives you some convincing, a somewhat convincing argument that this quantity here does actually give you the speed at which you're traversing this path. Okay, so how does this, well, you can now see that the speed at which of parameterization. So let's take a look at two parameterizations. Let x of t and y of t be the following. This is cos of omega t, sine of omega t. T, let's just make it an infinite time. And omega is a constant. What is the speed at any time t? Maybe the first thing we should do is to calculate we have a formula for speed here, it involves derivatives, so let's calculate the derivatives, right? So calculate what's dx dt in this case, and what's dy dt in this case. You want to do chain rule here, so the derivative of cosine is going to be minus sine, right? But then you want to do ddt of the times ddt of this quantity here, so that's an omega that comes out. So this is going to be minus omega sine omega t. And over here, this is going to be cosine omega t times, once again, an omega out front. All right, so the omega is from the chain rule. Okay, so now I want to calculate the speed, the square root of these two quantities, right? Minus omega sine omega t squared plus omega cos omega t squared. So it looks like the omega squared comes out, right? So omega squared factors out, and you can take the square root of omega squared, so that's the absolute value of omega. And what's sine squared omega t plus cos squared omega t? Right, so sine squared plus cos squared is always equal to 1, so that's just the square root of 1, so this is just the absolute value of omega. Now, does someone recognize what parametrization this is? What is x is cosine omega t, y is sine omega t? What shape, what curve is this in the plane? Yeah, so this is a circle centered at 0, radius 1, right? So we saw this last time, maybe you can review your notes. But this is a circle of radius 1, right? And what this is saying is for various constants, this is doing, let's say omega is a constant positive, let's say 1, all right? Then, cosine something positive, sine something positive, and t, this traverses it counterclockwise. If omega is 1, your speed 1. All right. If omega is something larger, let's say 100, then your speed 100. So you're still traveling up counterclockwise, but now you're rotating faster and faster, right? For larger values of omega. And this is how you see that, because when you calculate the speed of this parameterization, this is what you get, and your speed changes depending on the choice of omega you have for your parameterization, even though these all trace out the same circle. Especially if you restrict the range of t, you could all make it for each omega to traverse the circle once, just at a different speed. Maybe as a bonus question, if omega is, let's say, what's the difference between omega is equal to +1 and omega is -1 in terms of this parameterization? And yes, so to Dennis's question, yeah, if let's say I restrict this interval to -pi to pi, all right, then then if omega is 1, then I traverse then I traverse this one time. Whereas if omega is 100, then I traverse this several more times. And Ryan says, right, the direction, so the speed of, if omega is 1 or -1, the speed is the same, it's still 1. However, the direction changes. Because as we saw last time, by different means, just by calculating what these points are, cosine t and sine t is a different parameterization than cosine t and minus sine t, right? Sine of minus t is the same thing as minus sine t. Minus sine t gets you a clockwise, sine t gets you counterclockwise. So +1 and -1 actually then in omega would control whether you go counterclockwise at speed 1 or clockwise at speed 1. And similarly, at +100 or -100, in here it controls whether you go clockwise or counterclockwise at speed 100. All right, so well, speed is one of the things that is reflected in different parameterizations as well. All right, so now let's do arc length. So one thing that you might be curious about for any single path, right? If I have a path given to your parameterization, maybe I care about the length of this path, right? That's something that might be important to measure. Okay, so arc length is going to be, well, the length of the curve that's traversed by your parameterization. All right, so arc length of a parameterized curve measures length of the curve traversed once. So traversed once is because if I have something like a circle, right, then technically speaking, I could parameterize a circle and I could go around the circle many, many times, but I don't really want my circle to, when I mean arc length of a circle, but it's close, when it's a loop like this, then, I got to stop when I come back to the same point, right? I don't really want to traverse this loop many times and suddenly say the arc length is like several multiples of 2 pi r. That doesn't do me any good for a lot of applications I care about. The arc length, in this case, the formula is as follows. Suppose L is a curve with a parameterization x of t, y of t that traverses, or let's say with parameterization x of t, y of t with t between, let's say, a and b, that traverses L once. Then the arc length of L is as follows. The length of your curve is, given this parameterization, is your parameter from A to B, and you just want to integrate the speed, which isn't too surprising, right? Because once you agree that this is a speed, right, the only difficult part is agreeing that this is in fact the speed of your parameterization, which I hope I convinced you with my sketchy argument. Then, if you're driving along on this path and you see the speedometer on your car, well then, roughly speaking, if you just start your clock at A and then end it at B, then you look at each of the speedometer readings on your car, then technically speaking, if you integrate this, you sum these all up, that gets you the total distance that you've traveled in your car along L. So this hopefully doesn't seem too surprising. There's a question in chat. The only difference between velocity and speed is direction, kind of. So speed is always non-negative, and velocity adds a direction to speed. All right. So roughly speaking, you can think of speed as speed is always going to be the length of an arrow. The length of an arrow cannot be negative, and velocity is actually drawing the arrow of that length, and you could draw an arrow of a given length in any direction you want. So velocity gives you a more precise quantity. But we'll go over this, like I said, in a later chapter, much more detail. Let's go back to arc length. This is the arc length formula, and like I said, you're basically integrating the speed at each time. An important note here is, given two parameterizations, let's say x of t, well, I will do. So given any two parameterizations of L, they will give the same length in the formula above, as long as both parameterizations traverse L once. All right, so this is not at all obvious the first time we look at this, right? What I've said so far with this formula is you have to give a parameterization first of your curve, make sure that it traverses your curve just once. So if it's a circle, then you want to make sure that your parameter cutoffs here don't make you, go around the circle twice, for example. And then given this fixed parameterization, I'm telling you that the length of the circle is given to you by this formula here. Now, a very valid question is here, right? I've given you an example here where you can parameterize a circle however many ways you want with varying speeds, whatever you want. They're all going to give you the circle. depending on how you cut this parameter off. But the fascinating part of this is actually this formula here, which at first looks like it depends on your parameterization of your curve, which, as we know, as we've seen, you can parameterize a curve infinitely many ways. No matter how you parameterize it, this formula is the same. It gives you the same result. All right. The reason for this, you could do, roughly speaking, it's the chain rule. You write one parameterization in terms of the other. Let's say you have a different parameter, t tilde. You could write t in terms of t tilde, convert one into the other, and by a magical reason, all the coefficients here and here from the chain rule, when you convert this integral, it all cancels out and you get the exact same length. It's a bit much for this class when you write the proof down, but just be assured that it's a provable fact. You could write it down through the chain rule, through some computations, completely abstractly, and prove that this is true. But let's maybe do an example for the circle. Let me answer some questions in chat first. Is that the given same AB? No, two parameterizations of L could have completely different parameters A and B. In fact, they generally are going to have different parameters A and B. Let's do an example here. We'll continue this next time. So consider L as a circle. X squared plus y squared is equal to R0 squared. All right, so this is a circle of radius R, R0, centered at the origin. So for any, right, by the above, for any omega, constant omega, let's say non-zero, we parameterize L by the following. So because it's a circle of radius R0, not just one, cosine omega t, sine omega t, all scaled by R0. Now, does someone want to volunteer me bounds on t such that this traverses the circle exactly once? So this is going to depend on omega here, but in terms of omega, what are the bounds on t such that I traverse the circle entirely once? Once we answer this, we'll do the rest of this next class. I know we're almost out of time. So here's a hint, right? If omega is 1, I could just do 0 to 2 pi. So if omega is not 1, then right. So Mr. Goes correct. We could try 0 to 2 pi over omega, right? Because at t equals 0, for any fixed omega, at t equals 0, you start at 0, 0. So that's once again at the point R0. Let's say, right? So you're going to start here at t equals 0, no matter what omega is in this parameterization. And then at 2 pi over omega, t is equal to 2 pi over omega. You scale it by omega. So now this quantity here is going to be at 2 pi. So you've either gone this way or this way exactly once. No matter what omega is, you could fix omega. This together is going to give you a parameterization that traverses the circle exactly once, right? Probably at varying speeds, but this is true. Okay, so let me continue this calculation next time, and then we'll see what the arc length formula gets us.